Good evening, everyone. So today we are moving on to the day 6 of the training in FPGA development. So I welcome you all. This will be a recorded session, but don't worry, guys. Your questions will be clarified and your doubts are also be answered in the WhatsApp groups. Just message us in the WhatsApp Messenger. So let us go to the day 6 of training. And coming to the today's agenda, what are we going to discuss? So it is about to check the previous synthesized design about AND gate. So yesterday we have been recapping the AND gate. So today onwards we will go through the another example of simulation from complete flow, where you can upload the bit streams to the uh, FPGA board as well. So we don't have hardware with ourselves, but I will explain you how to do it on FPGA implementation, downloading the bitstream and uploading it. So let us start from today's agenda. So to check the previous synthesized design, I will take you to the example design with OR circuit again, synthesizing the netlist for OR circuit. Netlist, I'll explain what is netlist again. Some of you have asked it. And an entire flow of FPGA development will be understood here. Please make a note of it. You can pause the video and have notes, and wherever you got stuck, just let us know. To understand the flow of implementation and upload bitstream to the FPGA, these are the agendas today. So it is a complete flow, I can say. There are different other methodologies to develop on FPGA. We will discuss it in the later stages, but today we are going to implement on a regular flow, like developing the VHDL script, writing the architecture, and coming to the design implementation. After implementation, analyzing the synthesized part, simulation, and after simulation results, you're getting the bitstream generation and uploading that bitstream into the FPGA. So this is the entire flow. We will go through the flow by tool. So follow on from this slide to every slide that we go. Understand each interface. When I say interface, we are dealing with the graphic user interface of the EDA tool. What is graphic user interface? It is a window. It is what you see and what how you communicate with the design tools. So that is what graphic user interface. Examples of graphic user interfaces are MATLAB GUI designs, and some of the applications by Adobe are also GUIs. Every application that gives you tool access to appear on the screen in any OS, that itself gives you a user interface with everything. So that is a graphic user interface. So let us go to the today's topic, and we can start from an example project of OR gate simulation. So yesterday we have dealt with AND gate. In the same way, we generate design flow on FPGA with a simple example called OR gate. So let us go to the OR gate again. Open the Vivado, whatever version you might have, you can open this window every time. And what you can see is you can create new project. When you click on create new project, you will see the screen, and then open Vivado and click on next. And next you need to mention the name of the project. Guys, understand this flow. When you are too familiar with the tool, it won't be a issue for you to design any project as of a new thing. So start from doing things as I say. So follow on the windows or the slides that I show it to you. And now after you name the project, remember this orgate underscore project, because whenever you stuck at some point and when you want to shut down your project or system, and when you come back and restart it, you need to remember what kind of project you have named it. So there might be number of versions of the project in later when you go to the industry. So you should be remembering on the day basis. So in a day, if you work on 10 different versions of a project, you need to be so specific on what name you are working on, or else you might open a previous version of the project, which you don't want, which you have kept it aside for a draft working, and you will be working on the draft, not on the major project or main project file. So file name is very important. So please make a note of these project names. As of now, you are doing one project, there will be no hassle. But when you go for number of projects, there will be an issue. So take care of these minor things. These are very essential when you work in the industrial EDA tools. So after that, don't change any project location. Uh, Check with the project name. That will be fine. And go to the next best thing, that is this window, which shows what type of project you are selecting on. It should be like RTL project, because it has, as I said earlier, it has all the designs that you can develop in this type of RTL project type. So you can add sources. We usually add constraints file, or we usually add simulation sources. Any other types of sources we can add. That's the feasibility of this project type, RTL project. And it also has integrated tools like IP integrator. So it's another a block of the design. And generate, we can generate IP. Actually, we don't need to design an IP, but we create an IP and we can use it. So whatever IPs are present in the uh, FPGA chip or in the tool that you are using in the Vivado with the licenses included, those can be used again, reused, and we will discuss it in the later sessions from tomorrow onwards. So go to the RTL analysis and synthesis, implementation, design planning, and analysis. So this is a flow. So this kind of flow is the traditional method of developing something on the FPGA. What type of some application you want to develop? That's an architecture again. So kind of application development goes with the traditional method with this flow. And you don't need to mention any other thing. Click on next. And when you go to the next thing, right, you have set up the project name and the project type of the project. It's an RTL project developing on the FPGA. And go to the next window, you will see a window called add sources. Yes, to develop an FPGA, this is the first step. What is the first step? You need to add a script, whether it might be Tickle script, HDL script, or Verilog HDL script. So mostly it might be VHDL and Verilog. Don't get confused, guys. Verilog HDL is one kind of scripting language, and VHDL is another kind of scripting language. There is no much difference between them, except the syntax. I will take another class on defining what is the best difference between Verilog HDL and VHDL. It will be very beneficial if you learn both of them, or I would suggest Verilog HDL is the basic language you should know or you should learn when you want to enter into the VLSI industry. So understand the architecture development using Verilog HDL or VHDL scripts. So what is the main purpose of Verilog HDL or VHDL script? You can answer in the interview room by saying you will be developing architecture on any kind of processor or chip based on the specifications designed or architecture designed using VHDL or Verilog scripts and syntaxes. So that is the advantage. So you need to mention the source file. From there, the design development starts, and this is the first step, adding the source. So think it as a synthesis part, and this VHDL script addition is the first step. Make a note, guys. So then you need to mention by clicking on the plus icon, and when you say file type, and also name the file. Why do we name the file with r_gate? Just it is for our reference. When we try to verify the VHDL script or Verilog HDL script that you write, that will be verified using test bench scripts. Those test bench scripts will be again in VHDL or Verilog based on your main source file. So this we are adding main source file. Every design has a source file, which is main thing, primary source file, and a test bench source file. So don't get confused between two VHDL scripts. One is actual architecture development used VHDL, and one another simulation or verification script, VHDL or Verilog HDL script, is nothing but test bench Verilog HDL script or VHDL. So From here on, guys, I don't want to confuse you all. I will only say VHDL. Okay. So as we are working on VHDL script now, so as a summary point here, this is the primary source of developing the architecture on the FPGA. And for testing this VHDL primary source, we used to write a test bench. We will write it in few other slides in the next part of this lecture. Let us understand we are adding source. This is the first step. Make a note. So this is what you know, everyone. So VHDL OR gate, and click on OK and go to the next step. When you click on next here, and you will see the screen, add sources, and this is the summary, and you need to change the target language to VHDL, as I have already done AND gate on this. Now it will automatically take my target language and simulator language. So simulator language, it is mixed, keep it mixed, don't worry. But target language should be VHDL, because FPGA EDA tool Vivado will understand, okay, this script will be in the VHDL syntax, and if you make any error, it will give you a reference of that error in the VHDL syntax, according to VHDL syntax. And if you write in the VHDL script, and if you keep Verilog HDL here, and tool will take it as a Verilog syntax, and whatever you write in VHDL, it will be an error again. So don't make those kind of mistakes, guys. We are in the first step. As of now, this is adding sources. This is summary you have mentioned, OR gate, and make a note of this name as well, OR underscore gate. This will be used in the references in the test bench, and also in the declaration of the module in the VHDL as well. So click on next. After that, it will take you to the device selection. Now there comes a question from you all. I understand what type of hardware we choose. Again, I am repeating, we are taking an example of RTX 7 board. I will try to give this PDF of the datasheet of this board in our groups, to have a better understanding of the datasheet, how the datasheet looks like. In this lecture, I will definitely give you an explanation of the datasheet explanation. I'll try to open it and show it to you. But nevertheless, understand this step. This is second step, selecting the board. So when I say the steps, you need to make a note of that. First step is to add source. Second step is to select the board. How do we select in the second step? So you need to select the subfamily. It is RTX 7. What kind of subfamily? It has some processor subfamily to select on the board. This is the name of that kind of family, subfamily group. So in that subfamily, again, RTX 7 has different versions based on the package version, speed grade, and temperature grade, and SA revision. Everything changes according to this. But what we are choosing RTX 7, package CSG 324, and speed grade 1. Why? Because it's an ideal processor which has plenty of IO pin count and available. 1 second, guys. I can. Okay. So available IO bits and LUT elements. So LUT elements is nothing but lookup table elements. So we should have more number of these things, so then we can work easily, and we don't have any limitations if we have more number of things. If we have less number, we might search for a limitation. It is possible to design with the lower number of elements in the processor, but don't worry, guys, we are thinking of higher version, and we have higher number of flip-flops, higher number of block RAMs, DSPs, and then transceivers, and these are all additional parts of the processor. Transceivers, these are used mostly in the communications part. Every processor goes through a communication. If you add few of the elements in the communication side, these will be added on. So after you specify all these things, click on next, and you will see a project summary. By the end of step 2, adding device, so you will see a project summary. It should look like this. Then go to the finish. If you click on finish, and window will appear on the tool base. If you can see this, this is the tool, and it can show you in this way, where this is the third step in the design. You need to mention pins and ports, or ports actually. Ports have pins. So some of the EDA tools they mention as ports, and some of the EDA tools in the VLSI industry they mention it as pins. So when you go for a standard cell custom layout designs, nano cell designs, where you will actually design AND gate cell in the micro level, so at that time you need to mention pins, because uh, only standard cells have pins, they can't have ports is a group of pins. It's not declared anywhere in the textbooks or anywhere, but it is taken as a standard in the industry. So you need to mention port name as A, B, C. Remember guys, this entire OR gate simulation and design is a resemblance of AND gate. What is the only difference? Only difference is it has a lookup table that goes with the OR gate, and AND gate takes from the lookup table of AND functionalities. The truth table changes. Again, I repeat, when I say lookup table, please take care of that truth table. Consider it as a truth table, not more than that. So, uh, so this will be this step, and go to the next step now onwards, and you will be seeing the screen. Just understand, whenever you see this source file here in the EDA tool, you can check for the ORGate behavioral.vht, ORGate vht, it's a behavioral thing. Now you can see ORGate is produced. The general ORGate logic will be produced, but you need to add a simple line after the begin. Understand, let us understand VHDL script here. I will be making you an explanation on ORGate. Very simple. In VHDL, first you need to mention entity. There are libraries guys, libraries I didn't mention, I will show it in the later stages, but of the ORGate VHDL. Understand, the VHDL program or script, or the actual execution starts from declaring the entity. What is the entity? Entity is nothing but a device. Think it. And ORGate, this is what you have named the file as. So as per the file, it takes the name of the device as well. So what is the functionality now? What is the architecture now? Architecture is ORGate. So go to the port. The second next step is, in the VHDL, it is port declaration. As we all do, we need to mention A as input, B as input, and C as output. How did we mention this ORGate, this thing? It has been assigned by the VHDL script automatically from this step. Define a module and specify IO ports to add your source file. For each port, specified MSB and LSB values will be ignored unless its bus column is checked. This is a later step, some kind of advanced step that we will discuss in the later projects. But as of now, ignore this MSB and LSB. If you tick on the bus column, if you check it on this, then these will be enabled. It's a most significant bit and less significant bit. It's just a simple difference. So some of the pins will be subdivided into the MSB and LSB. So whenever you give input to the MSB, right, it takes in that direction, MSB to LSB. If you give an input to the pin that is connected with the LSB, it will take from left side, like LSB to MSB. So the data varies. It will vary if you say, for example, I'll make an explanation here. Very simple explanation, guys. 1, 0, 0, 1, 1, and 0. Let us say it will end with 1 again. So if it is your data message, I can't zoom in from here. Okay, that's not an issue. If it is an LSB, let us take a consideration. And if it is the MSB, and now you have A into 2 subdivided pins like A1 and A2, and if you give A1 as MSB and A2 as LSB. So it depends on the input of the data that it goes. So if you say A1 here as LSB, so the data counts from LSB to MSB at that time. But if you take A2 as input and A1 as the MSB, if you are taking A1 as the primary thing, it starts from MSB to LSB. So the data changes. So the message changes. There will be an error in counting or error in some application. So don't make that kind of mistakes, guys. So a simple explanation. There will be better explanation in the later lectures. Don't worry. So now you can see OR gate is added, and now you need to add this line. After that, AND OR gate. If you have said entity and you have declared ports, that is first step done. And going to the architecture. Now we are declaring, we are enabling the architecture feature of the VHDL script. To enable the architecture feature, you need to mention architecture, then behavior of the OR gate, and go to the begin. Every VHDL to execute a function like this, to execute the operation, you need to begin and end. What you need to end the architecture process. That's it. Behavior, end behavioral, architecture behavioral. Got it, guys? So it depends. In the later versions, you will understand the better code as well. When you write on your own, right, it will be better understood. So we will make you understand Verilog HTML as well in this entire training. Don't worry. As of now, understand this much. So you have written VHDL, and now you need to add test bench to the VHDL. Earlier in AND gate, after we write VHDL, we have written the test bench as well. In the same way, for the OR gate, you need to mention test bench VHDL file to test the functionality of this VHDL. So you have written the OR function. Whether it is working as an OR gate, you need to check it using test bench. So, and in the AND gate, just reminding thing, it is C and B. It's not C or B in AND gate. It is C or B in A or B in OR gate, A and B in AND gate. It's a simple thing, but everything is same. And there you have written AND gate, and now you are writing OR gate. Simple entity name. As you can see here, you are giving entity name, architecture name, behavioral. When you want to execute architecture, when you want to execute the function, you need to mention architecture, you need to mention, and then begin the process and end the process, if it is a process. So then go to the add source for simulation purpose. What is for simulation purpose? We are adding test bench file. Now in the same way, you need to add test bench. In this way, you need to mention it r_gate_tb. It is again entity name, and after you add it all, click on finish, and one second. So now go to the okay. So design OR gate. So this is the logic script of the VHDL test bench VHDL file. So go to the libraries. The actual VHDL starts from the declaration of libraries. It is a mandatory step, guys. How do we collect these libraries? It is a standard. Like in the C programming, if you have gone through, we are writing hash include stdio.h, conio.h, and iostream.h. So input and output. So it depends on the libraries. So why do we require libraries? Based on the libraries, based on the backend algorithms and libraries, we use some elements out of the library to make this function happen. So it is again understanding the algorithm backside of an EDA tool or any programming language. But the mandatory step, so you need to mention the libraries. It is a standard protocol. Just understand how to write and remember it, and you will write it anyway. Then come to the next lines. Same again, you mention the entity. First you need to mention the entity. Ports, it will be understood because you will map the ports in the later stages. This is the later stage. So now end the entity. From there it is defined. So come to the architecture behavioral. Again, you need to start from architecture again. In the VHDL script, to run the VHDL script successfully, you need to mention the architecture. It is the syntax. It is the syntax what it is. So component, you are telling the component or gate, and for that component you need to declare the ports. So what are the ports again in the VHDL to test? So these are the ports A, B, C and inputs. This we have to write. Why? Because we haven't declared them in the previous steps. We can declare it in the VHDL source file creation as well, test bench source file creation. But now here we are declaring and ending the component. Whatever you begin, you end it. So again, we need to mention the signals. This is the second step where you need to enable the signal flow through the pins. Whatever pins or whatever input pins, you derive the input to it and derive the output from that inputs. There should be a signal enable. If you don't declare a signal to it, VHDL won't be understood by the FPGA or EDA tool, and they will set this port number port C as an ideal thing, and it won't have any signal as well. So begin and duty. So it starts from DUT and OR gate. It's a syntax. You need to remember these things. Now we will be declaring the mapping of the ports like this. So one side it will be on your test bench VHDL and it will be mapped to the primary source file. So there is a connection between these two. So that hence the name should be same. DUT. So where it should be relate R underscore gate. Understand guys, it is not R underscore gate underscore TB file. You need to link it to the primary source file. That's where we mention entity as R underscore gate. So earlier if you see for this VHDL file, entity is R underscore gate underscore TB. But what we are mapping here, we are mapping ports for R underscore gate, which is primary VHDL file. And now go to the testing part. So it's like simulation. This actual simulation and verification starts here. Simulation. So process, you are telling. So now this is the process you need to execute. That's what you are telling to the machine or the FPGA through this test bench VHDL. Understand how we are giving the commands or set of instructions through this test bench VHDL vector or file. So give the inputs A, B, 0, 0 and wait for 5 nanoseconds. And again, after this clock period, you go for A, B as again 0, 0. You can mention 0, 0, 0, 1 and 1, 0 and 1, 1. You can mention whatever, however you want to declare it. Not an issue. I have mentioned 0, 0, 0, 0 again. You need to understand for the first 10 nanoseconds, it will be 0, 0, very low. And after 10 nanoseconds, the actual clock differs. I will make you understand this in the next slide. But before that, come back to the EDA tool. In the left menu bar, in the flow navigator, go to the synthesis, click on the synthesized design. By the time you synthesize the design, you will get a this file like schematic. If you click on the schematic, you will see this mentioned. So I will explain it with a simple thing. Come back to the flow navigator in the left side menu, go to the synthesis, and in the synthesis, click on synthesis design. You can run the synthesis first, then after you can go to the synthesis design. If you enlarge it, you can see the schematic. Go to the schematics and you can see the circuit window that can be opened. So what do we have in the circuit? How do we make EDA tool to create this circuit? We didn't design, right? We have designed in the VHDL. That is what we are doing since many sessions. So first we write the script, then we create circuit or schematic. We implement this schematic on the FPGA. Simple. Understand this flow and remember this. So after we write VHDL and test bench VHDL to it, so what we are trying to do, we are trying to make a schematic. Understand the schematic. Actually, it is created in the backend after VHDL synthesis. So now understand, you have input ports. This is the diagram of the ports. You can understand. And now let us see. So this is the buffers. Why do we need buffers? It's a protection element and it is a different delay element. Understand, it's very simple. Because if we enable the uh, uh, positive edge cycle and negative edge cycle in the on the board, right? It depends. When you click enable and when you click enable again, it will change according to the inversion. So if we give 1, it will take 0, and if we give 0, it will take 1 until you enable the buffers. So it's a predefined element before the port, because if a high voltage or high surge comes into the port, it shouldn't ruin your processor, this functionality. So every element inside it has a protection in it. So that is the use of it. Why do we need buffers? Such a simple explanation. So after we look into this, you can see this is the lookup table. So now understand, guys, what is lookup table? Lookup table is nothing but truth table functionality that is predefined on the processor. So this lookup table is only showing the OR functionality. What is OR functionality? The truth table of OR functionality. If you give 0, 0, what is input? We get input as output as 0. And if we say 1, 0, the output is 1, 0, 1, and output is 1. If we have 1, 1, you have output as 1. So it understands the flow. Got it, guys? Depends on it. How do we get 1, 1 here? We give input as 1, 1. So it is in the reverse process. 1, 1, 1, 0, 0, 1, and 0, 0. Understand? It depends on this flow. So you can see it on the screen when you on the board as well. Now, this is an OR gate simulation device after simulation. If we go through this design, but we can open in the window or layout as well. I will show it in a little bit. Understand the simulation first, and this is the timing diagram. This is the timing simulation till 10 nanoseconds. A and B are 0, and from 10 to 15, A is 0 and B is 1, and A is 1 and B is 0. After every 5 nanoseconds it is changing, and at the 20 nanoseconds it is 1, 1 again. Everything is 1. So such a simple simulation as you have done in the AND gate. So it is an OR gate. It is a repetition again. Now go to this GUI window. This is an EDA tool. Again, open this window, come back to the simulated design. After you see the schematic, right? Click on the RTL analysis in this left side menu and click on the elaborated design. When you click on the elaborated design, it will ask few questions. Click on OK, and you can say, you can see this thing, and then this OR gate functionality. Now, how did it change to OR gate symbol? It is nothing but elaborated. So it defines to the human understandable thing. And this is again lookup table. Don't think in other sections. It is a buffer to protect the elements. And now, in the industry, this OR gate will be connected to another AND gate or to XOR, to any other NAND or NOR gates. So it is not a single element anywhere in the entire design. It is a full chip. So or on the FPGA chip, you need to connect group of elements. So as we have seen here, the gates inside a block will be shown like this, and you can see how to view the synthesized design. So when you click on this design, you can see, if you zoom in to the blocks, if you zoom in like this in the GUI window, and you can see these elements when you zoom, and if you zoom furthermore, you will see this window. You can see how these elements are arranged. So these are the lookup tables inside it, and some multiplexers, some AND gates, some XOR gates. You can see all these elements. So they will be present until you use them. They are not in use. They will sit in the FPGA. That is the advantages. You have lakhs of gates or lakhs of cells, but you use few of them for fewer applications for the next 2 3 years. Then if you want to increase the use of more number of cells, then it depends again. You need to reset it and rewrite with the use of all the cells. Now go to the elaborated design. Why do we need elaborated design? Because if in the elaborated design you can see the ports, and these are all the nets are nothing but wires. This is net are connected wires between ports. Okay, understand, between elements you connect these ports and element using net. Very simple. So in that net, if you want to check the connectivity after the elaborated design, after the implementation, so I'll summarize the implementation flow again. But before implementation, go to the layout in the window for those ports. Check on the IO planning. Now in this IO planning, why do we want to do this IO planning, right? You have written ports on the script, and they have created this schematic as well. Now you need to make this FPGA Vivado tool to design these ports on the actual FPGA boards. So in the FPGA board, you have buttons and LED. Where are the ports? There are different ports. Now these buttons should be our input. So these input buttons should relate with the input ports of the logic gate. So now for OR gate is on the processor. Imagine, how do you give input? We give input on the buttons. When we click on button, it is 1. If we don't click, it is 0. So if we click both buttons, it is 1 1 again. I'm repeating. If you don't click, what is the output? You can't see any output. That is 0 0. So you are not clicking on the buttons. Where are you seeing the output? LED. So now I will write. So now it is like buttons. Okay. And this is a processor. Understand? This is the FPGA chip that you have designed this logic functionality. And now this is an LED. Sorry for my bad drawing. So this is an LED. If you click on both buttons, B1 and B2, you will be, if you click, it is 1. If you don't click, it is 0. What is the output you see after processing 1 0? You need to see 1, because it is a OR function. I'll got it, guys? Okay, so this is the functionality. Processor. Go to this window in the IO planning. Now what we are doing, we are assigning both the ports to the individual buttons and output port to the LED. That is what we are doing in the IO planning. So hence, after design implementation, you can see this step is to perform assign input and output pins to the FPGA. Now we are linking A and B ports to the buttons and C port to the LED. Very simple step. Before that, we have done the same simulation, very simple simulation. We synthesized the design. After synthesis and implementation, you can see the implemented design. And if you zoom in one of these things, right? If you zoom beyond, if you zoom again, you can see the logic cells. This is what I'm telling. Each one is a block. So I'll draw the outline. So this is a block. Got it? So in that block, you will see the cells. If you connect all these cells to their functionality, you can see the registers. After that registers, the set of operations can be ALU, or set of operations can do the memory storage, or set of operations can actually control the bus interface, everything. So it depends. Some will control the peripherals as well. It depends on the registers and logic cells. In the end, in the deep down, it will be seen as the logic cell operation. Understand? So now we are linking. Nice. Now after this IO planning, go to the add source. Uh, IO planning will open. That's not an issue. Open the IO planning and open the add source. Now we are adding constraints. By adding the constraints, we are actually declaring, okay, this port A should be button 1 and port B should be button 2. So port C should be an LED. Among LEDs, it can be one LED. So understand. So we are giving constraints now. In the beginning, we are not giving any constraints. Now we have to add the constraints. This is the next step. So out of 5 steps we have done, this might be 6th step. Please make a note of each step when you change, when you understand, when you go through it. So it is same when you add a constraint file, it is same as adding the simulation source file. Remember, now till now you have added only simulation source file. What it is? Testbench VHDL. Now we are going through the constraints file. How do we add constraints file? Same, by clicking on the add sources. Got it? So come to the next file, next window. It will show you how to save the constraints file. Make it as constraint.hdc. You need to name it. Name the file. Every file should be named under the project. Understand? Project is a folder. Inside folder, you will have files with .vhdl and .xdc. Understood, guys? One is primary source .vhdl or underscore gate .vhdl. Second one is or underscore gate underscore tb.vhdl. The third one is constraint.xdc. So click on OK. If you click on OK, it will be to the local project. So go to this window. Now you can see package after you add constraints. So you need to see this window down below in the IO port section. In the IO planning, when you click on IO planning from the layout, you can see the IO planning and then you can see the ports. Here we are assigning the ports. Okay. How do we assign? So we need to go to the data sheet again. So here in the data sheet, if you scroll down, we thought of giving port C output port to the LED, right? So to give LED, what FPGA pin it is designed in the FPGA by the manufacturer. Manufacturer has designed LED pin as a M16. You can give M17, M18, any LED you can use. You have 4 LEDs. Okay, 4 LEDs. You can use any of them. But as of now, I am using M16. So come back to this thing after you see the data sheet. Come back to the port C out direction and you need to mention the site which one you need to use. So that will be declared in the M16. See, in this site you need to mention M16. Got it, guys? In the data sheet, go through the data sheet, check for LEDs, LED section because we need to use, and you need to mention FPGA pin that is designed. So if you see closely, 16 and you have numbers here, ABCD or any other thing, and this 16. So one of the port will be sitting here. This is the FPGA chip. You're designing the chip. This is what it looks like. So if we go deep down inside it, now for the pin assignment, for the IO pin planning, right, it will say, okay, you can plan ground pins here. This is the ground symbol. And you can connect some of the ground pins for the logic cells inside the application, inside the chip as well. So how it will be connected. And again, some of the pins here. Okay, so now you have seen it, right? Now 16. Remember this 16 and somewhere M here or here or here M. Based on that row and column, you select that pin position and that will be assigned. Most of the times it will be on the border. So output port designed for LED pin. We never know. Here you can connect it somewhere here and you can you can see, if this is the pin for LED, right? Imagine LED is somewhere in the circuit here. I can show you. So this LED is connected to the pin of this. And how do you enable? This might be M16. Let us call this is M16. So in this column M16, one pin is connected to LED, but we need to enable. How do we enable? From the OR gate. Sorry, I'll read right. So if we design OR gate functionality here, if this is the output port C, and this C is connected now, this port is connected to this pin. Now we are planning the IO ports like this. That's what we are doing. And this OR gate is again lookup table. Don't worry. I have just given explanation in that sense. So now output port is done. Now come to the next thing. We will be seeing another Excel sheet based on the design. How we will be seeing this Excel sheet. It is all provided. This data sheet, this data PDF, and this Excel sheet. All these elements are provided by the manufacturer itself. So we don't want to worry. These are available in the website of your purchase. If you purchase from Amazon, you get a box and they have their own website of manufacturer. And in that manufacturer's website, you can find the datasheet. So our name is Artex. So our device name, you can see Mars AX3 user manual. Datasheets have this name user manual. So Mars AX3 is our board. Okay. Index Artix 7 is the FPGA chip type. So the 4 LEDs on the Mars AX3 FPGA module. Now you understood? The 4 LEDs on the Mars AX3 FPGA module are connected to the FPGA logic and they are active low. Basically, they will be active low. Until you enable, they won't be active high. So come to this Excel sheet for the pin assignments. If you scroll down, you can see the voltage as U1 and V1. You can assign these pin names. You can use any of them, but as of now, we can choose this one based on the Mars AX3 Artix 7. And this is what voltage pins. Ground pins are different again. So based on the M16 LED, which one is the nearest one? Based on that, you can use it. You can choose a random thing, but ideal element of use U1 and V1 as of now. So if you connect those things, you can select here. After this selection of these pins, you need to go to the IO standard. Now what is IO standard? Here we are declaring the voltage for that port. How much voltage should be utilized through that button and through that pins to make the LED happen. That is millivolts, 3.3. 33 is nothing but CMOS 3.3. You need to drop down the menu and check it. LV CMOS voltage, CMOS 3.3 millivolts. So it's in the another reference of the units, but you understand 3.3. Got it? VCC voltage. Okay, we don't have V reference, but VCC. In the normal circuit diagrams or analog circuits, you can understand the transistor connections, right? You have VCC and VSS, like, or VCC and the ground. So it depends. VCC, that is LV CMOS. Okay. So you need to declare these two IO ports, and then if you click on Control S in the window, if you click on Control S here itself by clicking, you will see the window here and save it. Select an existing file. You need to save, or you can save it as a different IO constraint file. Sometimes in the process design, right, you will be checking as two constraint files before IO planning and after IO planning, because when you have done a wrong IO planning, you need to delete this file and you are not interrupting the original constraints file. So that is an ideal practice. But as of now, I want you to overwrite on this thing. But it is a best practice to save your original files. Again, another tip as an engineer. So you need to save the primary source files every time as a backup. You never know when you are designing, your laptop can go shut down and you can't save the existing process, existing procedures and work. But you need to have a backup every time. So when you accomplish some task on project, you need to save it immediately in a separate folder such that you will have backups. And now industry is introducing you for the server based backup, and those servers will also be ruined at sometimes. And industries also have cloud based backup, again an online backup. So you need to back up your work instantly at particular intervals of task completions. So remember this point. It's an another thing. As I have said, you need to mention your file names very appropriately to make a reminder. And again, this is the second step. You can overwrite on the existing constraints.exe file, or you can create new file and you need to map it again. So after the constraints file got added, if you click on OK, you can see these constraints are created by the EDA tool. That's what automation is. You can write these constraints by set of XDC, like this is another script file which has commands. So set property is a command. So set property that port or some voltage pin are properties, and that package pins are again connected with the FPGA pins. And property voltage we are declaring. After declaring the voltage, we are going through the pin declaration. Actually, FPGA has pins, right? That processor pins, and that processor pins are attached to the ports. So get ports is a command where get port C. I'll make a writing. So get port C. Understand the command, how it works. Set property. We are making a command. Okay, FPGA. Now understand. I am setting a property. What kind of property I am setting? Attribute property means. So take the port C, get port C, and connect it to the M16. This already I have done manually in the IO ports planning. Now I am checking in the XDC file, because this XDC file, this test bench VHDL and VHDL, all these files will be moved to the bit stream, and that bit stream will be sent to the FPGA processor. Bit stream is nothing but, imagine that it is a binary file. Okay. Now you can see this command. In the same way, get port A and connect it to the U1 of the FPGA pin, V1 of the FPGA pin. And for these ports, you need to declare the LV CMOS voltage 3.3. That's a name nomenclature for making the FPGA understand the voltage. So again, erase all hints. So now go to the next part. Now you can run implementation after you check the XDC file. If you click on run implementation in the flow navigator, you can see, click on yes. It will ask the basic verification question, and click on yes, and it will take you to the process. The design will be initialized, synthesis is done, and after a particular time, it will ask for new version of the synthesis. Every time you need to synthesis. When you change something in the design, the synthesis should go, you need to run the synthesis again, and then after you can go to the implementation. That is what it is happening. After synthesis successful completion, it will take you to the implementation process. Wait for some time. It might take around 1 minute. Then after successful implementation of the design, it will ask you to open implemented design. Click on OK. Now again, you will see this window. Okay. Now you are seeing this window. Very good. What you need to do, it is same as the previous window. After you click on the device, go to the implemented netlist. This is the netlist. Netlist is nothing but all the ports and the elements are connected with the nets. and you can see these connections in the netlist file. That netlist file will ndc. This netlist file will declare the net connections, and if you select all these ports, and if you click right click, you can highlight them with whatever color you want. So I have highlighted with the green. So in the next window, you can see the actual connection between output and input, or input port with the output. So this might be U1 and V1, and this might be M16. So I will show it in the next window. So see, this is the M16. Wherever the arrow ends, right, that is M16. M16. This is the pad. Simple, guys. This pad is connected to the LED. Pad is nothing but it is a term for the port where the actual soldering or the actual material lies there for the conducting thing. This pad, we call it as pad, that area of 1 micrometer or 1 nanometer. So that is pad again. Pad has again, it is embedded in the ports. So M16 is the pin. Now M16. So this is output. What is input? You are coming from U1 and V1. This is how pins are connected. Inputs are connected. So here you have inputs, U1 and V1. You are connected. You can connect U4, L6, L5, anything you can connect. But you have utilized this thing, this part. So if you can see, this looks in the zoom out version. If you zoom in to the leftmost part here, you can see this thing. And next, you can see the inputs are connected in this way. So now after the design closure, you can see in the implementation, if you can go with the flow navigator. If you click on the generate bit stream, now at the final part, this is the final step, go to the generate bit stream, and if you click on bit stream, you will see the bit stream generation successfully completed. View reports. So if you click on view reports, right, you will see the reports in this way. You can open each report. You can see the timing report. How are the nets connected? What is the power report? Are the power of the pins and inside the chip, if it is working at the 3.3 millivolts. So everything you can see. This is the flow again. First we synthesize. Synthesis has reports. After synthesis, you get the summary of the reports. After optimization, it is again the internal part of synthesis. Then we go for the place design implementation. This is all implementation. Place design route. Place and route is the design implementation. Then after place and route, again it should go through the optimization. Wherever the optimization comes, it is connected to the previous step. Understand? Synthesis, design implementation, and verification. Write this bit stream. So that is the end part of the log. So this Vivado, it will generate the bit stream. Now what is the bit stream? So bit stream is nothing but a file which actually converts your entire code, entire language script, or entire the connections and the functionalities that you have assigned in the architecture. All these port connections, XDC files, and the input VHDL files, all these will be connected in the bit stream, and it will be connected it will be converted into the IO ones and zeros, and then that will be uploaded to the FPGA machine. So only hardware understands in the binary language. So that kind of bit stream generation. Bit stream is the name itself has, you are giving entire data in the bits. So generate bit stream. It will ask for the view reports. After bit stream generation successfully, it will give you a reports, because you need to check the reports before you need to go through the reports. I didn't open any of these reports, but these will be existing in the file in the project of yours. So after these reports are generated, you need to check these reports. If you see any anomaly or any error or ambiguity, if you possess, you need to go through this bitstream files, and if you need to go through the source files, you need to change them and you need to come back. So that is all debugging and error rectification. So we don't have a target, guys. Now that is bitstream. The final step is upload this bitstream file, whatever the project you have developed, You made it into binaries, 1 zeros, and this bit stream you need to upload it to the FPGA. How do we upload? We connect this pins to the FPGA. So this is the port here. So we need to connect the USB to the machine, to our laptop, and to the FPGA machine. So here itself you can see the processor. It will be lying here. So, and when you upload the bit stream, right, you will open the hardware manager. How do we upload bit stream? You can open the hardware manager, open the target. It will pop up a machine, whether it is a local host or a server, remote server. If you have hardware, connect the hardware, it will automatically detect. And if it didn't detect, you go to the device manager and check it in the COM ports. Whether you might need to check with the USB wire that you are using. If it didn't support 3.3 volts, millivolts, then you need to change the wire. There will be issues with the hardware. I'll come back to that. So you need to connect the USB wire, and you can see these are the buttons. If you click on these buttons, right, I mean power and ground buttons, that is not an issue. LEDs, and if you click on buttons, right, if you click on one of the buttons, and you can see the LED blinking here in the board. We don't have board in our hands. That's a drawback, but you can understand. So this is what the flow is. In the industry, you won't be directly dealing with the hardware. You will be dealing with this entire flow. How do we know for sure this hardware entire language is working? These VHDL files are working. We have verified thoroughly with 2 steps. One is the simulation. If we recall, this is one simulation step. The actual VHDL or primary source is working. Then we go back to the test bench VHDL that is already there. That is another step. And in the third, we can check with the connectivities. So these are successfully connected. If it shows any error, you need to rectify it by debugging. So after report. So that is how we upload the bit stream. This is what the board looks like. And Enclustra, you can go to their website and you can search for the board. RTX Mars AX3 is the board name. You can search. And this is an example board. As I'm saying, you can see if you give this input as 1 and 1, you can also enable the LEDs 1, 1, and you can see the output 1 again for the OR gate. Or you can enable one of the LEDs. You can see this might be, there might be one LED in the device where it is. And also you can enable the LCD display as well. These are the IPs you can integrate on the FPGA. Very simple process. I will explain it in the later stages. So that's it, guys. Any questions, please come back to us in the WhatsApp chat. And then thank you. There ends the recording. So Jai Hind.